Okay, hello, welcome to another walkthrough. Today I'm going to be quite ambitious and I'm going to do a walkthrough of the case Origami, which was the final case in the final of the Microsoft Excel World Championships last year, 2025. Pretty very difficult case. And yeah, I'm going to give it a go. It makes sense to do it this week because it was the community case this week. I have gone through this now a few times, worked out my best approach, kind of end up doing something slightly different each time that I try it. But anyway, hopefully this will all come out good in the end. And yeah, not really much to say. I'm going to assume you've seen the case or you're about to try it or you have tried it and you're just looking for ideas. As I've said, this is not how I attempted it the first time through. This is me having gone through and seen how best to approach it. So that's lots of initial chat. Let's get on with it. We're already almost at a minute. So let's go to level 1. So we're given a reference in here. We need to find the corresponding value in here. So we can actually just do this as a single X lookup as long as we call each of the ranges. They then become a single column and then we can just perform a single lookup next to each of those. So that's nice and straightforward. Level 2, we are now going to go into our data tables. We're given a size of a kind of square and a center square. So we need to work out how to offset from that. So what I'm going to do is I'm going to work out the size of the offset, which is going to be the value in B1 minus 1 divided by 2. Because we're going, so if it's 7 is the total size, then 3 either side of our central cell. So I need to create a sequence of the value in B1 and then starting in the minus the value that I've just created. So go from -3 to +3 and doing the same thing over here, but going along the way. So again, B1 starting at minus E4 and then I'm going to get my cells, which I'm going to do as I'm going to do my offset cell address lambda, which if I import those and I bring in, so if I say offset cell address point at C1 and then my row offset is that sequence we've just created and my column offset is that sequence. We get all of the references from HV20, HY123 is in the middle and then IB126 is over here. And then just for the purposes of making this easy to see, I'm going to then just do my address lookup. Actually, I haven't named the range, so let's go to the sheet of paper, select anyone here, call this MP. And go back to level 2 and then I'm just going to use my address lookup on this range here, which gives me, I didn't actually give it the map, which would help. And then we are asked for the total, so I can just hopefully sum up everything in this range here. And we get all of our answers. That's good. Let's go on to level 3. We're going to do something similar, but we're going to start folding. This time we're not given variable size. We're just given a single size. So our sequence is slightly easier. So it's a sequence of 8 starting at 0. And this time we're starting at 0 because we're given the top left-hand corner of the range, which I think is the same all the rest of the way through. So again, 8 to the right in 0. So now I'm going to use my offset cell address on B1 using my row offset and my column offset to give me the whole range. And then let's see if I can wrap this straight into my address lookup based on the map. And that gives us the actual values. And now we need to know which one we're doing within that. So for this, I'm going to use regex extract from this kind of row column reference. We want anything that is a number, and it could be a double-digit number. So we get 6 and 6 for that one. So we're then going to index into this range here based on this row and this column, which in the example gives us 11. Oh, we haven't actually flipped this yet. So what we need to do here is I'm going to apply my flip array lambda, which I have, so I can flip an array in any direction, and I'm going to use we're flipping from left to right, so I'm going to use my right arrow, which I've got saved as a kind of defined name, so _r is just the right arrow. So we flip that, and so the one that was in the 6th row is now this one here, and so I can just point to that, and that gives me all my answers. So level 4, and I should point out I'm using a flip array, even though we're technically folding it, but up until level 6, we're actually just flipping it, and it doesn't matter that the other half is still there. We haven't covered anything up. It's only in level 6 and 7 we then have to deal with the concept of when we fold, we actually move something over to the other side and we cover it up, and we'll get to that. So level 3, that's nice and easy, all straightforward so far. Level 4, we're now given a variable size again, and we're given the top left hand side, so we need to know our cell offsets. So actually we don't need offsets because it's still from the same, but our sequence will be slightly different each time. So the sequence is whatever's in B1 starting at 0, and our columns is the same sequence starting in B1 and going, the number is the size of B1 and then starting at 0. So then I'll go my offset cell address from C1 with my row offsets and my column offsets. And then we want to look up those values. So I'm going to wrap that inside my address lookup lambda, which then gives me the actual values. And then we're going to flip it based on the arrow that we're given. So let's wrap this inside flip array. The array is already what we've got, and then our arrow is what is in D1. And so that flips it. So we'll just check that against here. So there's middle row is 14, 3, 8. Yep, that's fine. You can see we've still got these numbers here, whereas in reality we shouldn't, because we've effectively kind of moved them up. But anyway, that's doesn't really matter for now. It only matter in the level 6, as I said before. So what do we actually ask for? We're asked for just a reference again. So we're going to regex extract from E1 anything that is a digit, possibly double digits, and then we're just going to index into our array, which is this, based on these two numbers, and we get 19, which looks good based on the example. And yes, we're all good. Okay, level 5, we're now introducing double folds, which again doesn't actually matter that we're losing numbers here, because it's just the same as flipping once and then flipping again. So we still don't have to worry about anything at this point. So actually I could probably just, well, just for practice sake, we'll just keep doing the same work. So we're doing a sequence of B1 starting at 0. Our columns are a sequence of B1 starting at 0 but going to the right. So our cells are the offset cell address of C1 based on these row offsets and those column offsets. We're then going to wrap that inside an address lookup, which is looking up the map based on those cells, which we get all of our numbers. So 4, 10, 6, 18. Yep, that's good. And then we're going to now wrap this inside a wrap and a flip. We need to work out what the flips are. So we're going to regex extract on D1, which is our arrows, taking any value, which is basically what we will get. We'll get our arrows. That's brilliant. So we get a right and then a down. So I'm just going to wrap this in twice, which is not the most. Really, I should be using reduce to go over this. But we flip it to the right, and then we literally do the same thing again. Flip it this time to down. Because we're always just doing one across and one up and down, we don't need to worry about the fact that these numbers would technically disappear. But we've got these same bottom right hand quadrants. So all we need to do is grab our references, which again from here, any number, and then our index will be index into the array, looking at these two figures. And if I hadn't actually done the setup work, I could have just copied this over from the previous level. It would have been fairly straightforward. And we get the answer 4. And we've done level 5. We're on 8.5 minutes. So yeah, we're going to need all this time because this is quite tough now. So into level 6, it now gets very difficult. So I'm just going to quickly build. Actually, let's get some of the same work from previous. So we're actually speeding things a little bit up. So copy that all over. This is no longer going to work because we're now just dealing with one flip, and our arrows have moved. So let's get rid of one of these flips, and let's change that arrow to point at that. So we've done our flip, so we've moved everything. So 20 is now in the top right hand corner and across the bottom, but we don't actually want to keep these kind of diagonal numbers. So we have to do what's called creating a mask, and this is probably the most difficult part of the whole project. So we're going to create a let. We're going to have a let, an array, and we're going to have an arrow, and our arrow here is that. And then what we need to do is we need to create a mask, and I'm going to extend the formula bar so you can see what I'm doing here, because this is the tricky bit. So I'm going to have a mask, which is a bunch of if statements. And we're going to say, depending on what the arrow is, then we're going to do something. So in the first case, we'll go arrows equals up. And then I'm just going to copy this. I'm going to copy this a number of times so that we can then work out all of the possible options that might occur based on the 8 different directions we might have. So we're going to have up and down, we're going to have left and right, we're going to have up right and up left, and we're going to have down right and down left. And depending on which of those we get, we will then have output our mask. So for the moment, it shouldn't actually produce anything because we haven't given any conditions and we haven't told it. We have given it an arrow and we have given it an array. So we need to also put in a couple of other things here. So we need to know the size of the array. So that will be the number of rows in the array. And then I'm going to create a sequence of rows, which is just going to be sequence of size, and a sequence of columns, which is going to be a sequence of size as well, but with a comma in there. So we then have our kind of columns going along the top, and basically everything here is going to be some variation of columns and rows. So if the arrow is going up, then basically we want to keep everything or mask everything in the top half. So we fold it up so we keep everything. So what we're going to say is if the row is less than or equal to the size divided by 2, and for the moment what I'm going to do is I'm going to temporarily change what I'm looking up. So I'm going to grab, to make this easy, I'm going to grab a bunch of arrows. I need to put an underscore there. I told you this was the slowest bit, and then I'm going to give a number and I'm going to give an output which is just going to say index into this based on that number, and then we can test each one as we go. So now my arrow temporarily is just going to point at this. So let's start with the 2 because that's what we had, and we can build these. So if it folds up, we want to keep everything in the top half, so that looks good. So we'll just wrap that in a minus minus. Okay, and actually what I might do is I might just say row plus column times 0, just to put that into a proper mask. Okay, I'm going to copy that. So when it's down, it's going to be very similar, except it's going to be less than s over 2. When we do down, oh no, not quite. So what have I done wrong? Less than, no, it should be row times 0. No, I want it when it is greater than. There we go. So that's working. Let's go on to left and right. So when it's left and right, let's think about this. This, again, told you this is the slowest bit. So when it's going left and right, we're changing these. So it's the column and the row are slightly different. So when it's left, we're currently on right. So let's go left. So when it goes from the left, okay, so that needs to be the other way around. So it needs to be less than or equal to. So we keep everything on the left. Good. And so let's go to the right, which will be the same basic structure, but we're changing that to greater than. Yep, so we've now got our mask. So if I change that to 1, 2, 3, 4, we've got each of our masks. Let's go on to the next one. So 5 is down. So now we're going to start dealing in diagonal. So let's just put column plus row. And we're actually on down left, down right. So let's do that here. Column plus row. We get that. And so when we're going this way, we want to keep everything above 7. So we're going to say column plus row is greater than or equal to size plus 1. And we want to wrap that in minus minus. And that's our mask there. So then when it's going the opposite direction, so up left, it will be something similar, except it will be less than s plus 1. So let's change that to 6. We're 1 off because the middle row is not going there. So we'll say less than or equal to. There we go. So we're almost there. So let's go on to the last diagonal. So this one is going to be, that's going down left. Let's go to up right so we can build something. So it's no longer C plus R, it's going to be C minus R. And it's based on whether it's greater than or equal to 0. So when it's going up, we want to keep everything that's greater than 0. So we'll say where that is greater than or equal to 0. That's good. And then we'll go to the last bit of our mask, which is down left, where we'll copy this and we'll say where it is less than or equal to 0. That's good. So we've now got our mask working. So we put in an array, we give it an arrow, and everything else follows through. So what I'm going to do is I'm going to OA robot this, call it let lambda, which it should handle quite nicely. Yep, and then we'll just say save lambda as, and we'll call this our mask. Okay, so this is creating a mask based on the size of the array. So that's taken at least 7 minutes, crikey. That's even trying to go my fastest. That's all I can do. So we flipped the array. So for this question, all we now need to do is actually multiply the flipped array by that. Have we flipped this array? We have. Oh, but the arrow is pointing at the wrong thing. So our arrow should be pointing at that. So we've now got the top half, and then now we need to find out this kind of equally awkward thing of getting the quadrants. So there are 4 possible quadrants. So let's just say we've got up left, we've got up right, we've got down left, and we've got down right. And what I'm going to do here is I'm going to use my scale up array, where I'm going to take this array and scale it up this number of times divided by 2 and do that twice. So what that does for us, 1 of 6, it makes it 6 by 6. And then I'm just going to say, does that equal the quadrant we're looking for? And then I'll wrap that in minus minus. And then what I can do is just say times this by that. And we now just get the final quadrant we're interested in. And my answer can just say sum on that. Okay, and we've got spill error because I haven't given myself enough space, which I did during the workings out. So I'm just going to add in extra columns until all of those answers are correct, and then we're good. Okay, moving on to level 7. Let's grab some of those workings to start off with, and then take it from there. Don't think actually we need any of that. So we're starting off with our normal array, and we've actually already done the first flip, which it doesn't actually know because of this is pointing to something that doesn't make sense. So let's get our regex extract our arrows. We want every arrow possible, and let's point that first one to there. Okay, so this is our first fold, which is a downward fold, so 12 down at the bottom. And then what we need to do is we now need to apply the mask to this. So we also need to say, I'm going to try and do this slightly different to how I've done before. Actually, no, let's do this let's spread it out just so you can see the working. So then what we want to do is we want to mask this array by the same arrow, and multiply it by that as well to give us, so that's our second fold. Okay, so what I might actually do, I might just, although you should probably use a reduce where you do this multiple steps at a time, I'm going to show you myself doing it in the 3 steps, and then we'll just expand it so we've got space for all the spilling. So we've then done our first fold, which for the first fold we don't need to worry about a secondary mask where stuff can fold over stuff that already exists, but I think we should probably take that into account. So I'm going to say let that be, I'm going to call this the top layer, be that, and the bottom layer, the stuff on the bottom, is going to be a mask of the array using the same arrow, but times, now let me think about this, mask of the array, see that's not the original flipped array. Okay, let's try this slightly differently. So let's get this as the original array. Yeah, thought I might get myself confused. So this is the original array, so let's do fold and mask at the same time. Fold and mask. So what we're going to do is we're going to say let top layer, let's say top layer be, not op layer, top layer be the flipped array of this times the mask of this based on the arrow. And I need to give an arrow to the flip array as well, and I probably should define those as let's just call that the top layer and see what we get. Yes, we get that, but then we also need to take into account the bottom layer, which for this first one won't really make sense, but it will on the kind of third fold. So the bottom layer is the original array. Bottom layer is the original array times the mask of the original array with the same arrow. And if I just say bottom layer, I've got too many brackets, but if I just get rid of one, nope, something's gone wrong there because it's then tried to apply a random multiplication. So that's what was underneath. Excellent. And so what we're going to say, our final bit of logic, and this is probably one of the toughest bits of logic, is, let me think about this, if the top layer equals 0, then we take the bottom layer because it's not covering anything up. Otherwise, we take the top layer, which for this first one won't really make any difference. Have I done that wrong? Top layer. Okay, it doesn't like that. Let's try that again. So top layer. Again, it's inserting random multiplications. Don't like this. Top layer. There we go. So the top layer is what's been folded. That's fine. The bottom layer is the kind of original version. So yeah, so we're saying if top layer equals 0, then we can actually just see what was on the bottom layer. Otherwise, we want to see the top layer. There we go. Okay, and that's going to do that once. So let's say, yeah, how am I doing for time? Okay, do I need to turn this? Should I turn this into a lambda? No, let's just do this next one. Let's just copy this over here. So that's basically the first fold. So the next fold is going to be based on the array that we've just done. So let's just put that over here. Again, I probably should have been neater by naming this more properly, because I'm going to have to do this multiple times. Putting that into there. And that gets the second layer, which matches what we've got here. Brilliant. And then let's just copy that over one more time. Again, it's going to give me a bunch of errors because I want to look at this. Oh, actually, I'll tell you what. If I do a little bit better copying and pasting, if I copy it, that some of it will already be lined up, and it's just these arrows that I need to line up. And then we should have matching on that final layer, which we do. So then we can just say equals sum of this, and half of them are going to come out errors because I haven't left enough space. So what I just need to do is add in a bunch of columns until we have enough space. In fact, let's go to 1, 2, 3 just to see how much space we actually need. Okay. I'm sure I could add in more spaces more quickly than my keyboard shortcut. There we go. Alt-IC, just inserting a column one at a time. Not particularly efficient. But there we go. Let's just do one more just so it's nice and neat. 113 is still not showing us enough space. So we need a couple more columns. I think it's 2 more for each. Is that enough? Yes, there we go. Okay, right, 23 minutes. Oh, this is going to be a real struggle to get this under 30 minutes, which would be a shame. So the sum of the main diagonal, that is going to be m unit of the rows in the map times the map, but I need to wrap that all in a sum. Oh, and now it's crashed. Is that because my data table is doing too much work? Okay, I'm just going to pause while I wait for it to wake up. Okay, we're back. My Excel had a full-on meltdown, but I think I sort of gave it too much work to do. So we want to take the m unit of the rows of the map, close that down, times it by map, which will give us a spill. But if we sum that, we will get 2574. What is the sum of the 4 central locations? So if we said 256 divided by 2, that's 128. So we're looking for row 128 and 129. So I'm going to say the sum of the choose. Oh, how if I put it equal? So sum choose rows. Choose cols, doesn't matter what order I put this in the map, 128, 129, and then 128, 129, and we get 46. What's the largest sum of numbers found in any 5x1 vector? So this is a really good place to use the by rectangle lambda. So we take the map, we're going for 5x1, and we're summing them. And then we're doing the same again by rectangle, taking the map, this time 1 by 5, and summing them. And we get 98. Always folding from left to right and considering each fold reduces the size of visible cells. What's the sum of the visible cells when we reach 4 columns? So what I did here was I'm going to do a sequence of 256, and we're folding from left to right. So basically we're folding this top half, let me think about this, left to right, top half onto the next half. So yeah, we're going to take the top half. So what we want to do is take from this, the number of columns in that, but divided by 2. And that's kind of the first half, but it's now been reversed in order because of the way we folded it. So we do that, and then we're going to just keep doing this until we get only 4 columns, which ends up here. So columns 85 to 88. So we then want to sum, choose cols of the map based on those 4 columns. I don't think that reference has actually worked because I didn't put a sum in there. Let's just type in 85, 86, 87, 88. And we get 10584. And then what is the center cell of the only 3 by 3 that contains all 1 to 9? So we need to go to the sheet of paper. Got 4 minutes. Can I get this done? I think so. So I want to imagine I'm building a lambda. So I'm going to say, so let's take lambda. We've got a range, which is 3 by 3. And then what we're going to do is, no, let's put this as let. So let R be a 3 by 3 range. Then we're going to sort R in order. No, we're going to sort the 2 col of R. And then we're going to say, is that equal to a sequence of 9? Because then they're side by side. And if that were true, we would get a true. So I'm going to minus that, so it's a 1 or 0. I'm now going to turn that into a lambda. So I'm going to say R is my variable, and I want to be able to apply that to the whole of this range. To help if I could type lambda. Actually, that doesn't need let because it's actually just a single thing. And then I'm now going to use my by rectangle again on the whole map using that as my lambda. But I need to say 3 by 3 is my size. So I then get, and we'll see there is a 1 there. So we just need to work out where that relates to in the real thing. So I'm going to say if that's true, then give me the cell address of the map. Otherwise, just return nothing, which can be a bunch of errors. But then if I put that in a 2 col, put a 3 at the end, I get my actual cell. If we go to cell J33, J33, we see that that's the top left corner, but they actually want the cell in the middle. So K34 is our answer. So K34, and we've done it in 27 minutes, 48 seconds. Did about a minute of talking at the beginning. So just, 27 minutes all told. But you can see why that was the final case. The original game, they were given 40 minutes to do that. Even then, I think on your first go through, that is a really tough ask. Like I said, the hardest bit is this 2 concepts. The flip, I guess most people probably got some version of a flip array lambda, so that's not too difficult, although you could try doing it manually, which playing around with sequences and indexes and stuff, which for left to right and up down is not too bad. For one of the diagonals, you can just use transpose because that's the exact same thing. It's the other diagonal, which is a little bit tricky because you have to reverse and sort. But if you've got a flip lambda, that does the work for you. But then this mask bit is really tough. And manually setting this up, which you saw me do there, took 7 minutes. And that was me trying to be quick as well. So the mask bit was tough. And then in level 7, it's also this bit that you have to, where we had it here, where you have to kind of consider the top layer and the bottom layer. So in the example, when we fold over this bottom triangle over the top, the original bit, the bottom layer is still visible. It doesn't change. And that was, again, a concept that becomes quite hard to follow in that last level. But yeah, great case, fun case, really, again, something quite simple ultimately, but leading to a lot of complexity. So great case, learned a lot. And yeah, good work. Hope you enjoyed it. I found it helpful, learned a lot, and see you next time.